Thank you, Ms. Gina, for your nice introduction.
Thank you so
I
much.
would also like to thank Dr. John, who had been with me all the time, and he guided me and he supported me, as a result of which today I am speaking to you. Thank you very much. This is the first keynote speech, and you know, the well-known English proverb says, first impression is the best impression. So if this talk is inviting to all of you, I hope this whole Congress would be successful. My talk titles, Advanced Supported Polyolefin Catalysts, Innovation and Challenges. I'm a senior research engineer and also a professor at the Center for Refining and Advanced Chemicals, the Research Institute, Fahd University of Petroleum and Minerals. Now, as per the guidance given to us by MatScience, my talk is going to focus on research journey, challenges, inspirational lessons, and creativity. Okay. Now, how we did start our polyolefin catalyst journey in our center. This slide introduces to you the Saudi petrochemical polymer industry growth profile. It is covering a period from 1976 till the projected period 2025. You can see from the slide that the petrochemical polymer industries in Saudi Arabia is now numbering 20, and the total production of polyolefins is 16.25 million metric ton per annum. This journey began first in 1976 with the establishment of Saudi Basic Industry Corporation. The journey progresses, and you can see that between 1980 to 1985, the kingdom established another 7 in 93, 1, 96 to 2003, 2001 to 2005, another 5, between 2006 and 10, another 7, 11 to 15, another 4, 16 to 24, and now 2015 to 2025, there will be 5. So the total number of petrochemical industries, companies, and complexes that Saudi Arabia feels proud of today is 37. Definitely this credit goes to the administration of this country, the leaders of this country, and their strategic planning, farsightedness, their feeling, and sincere commitment to take the nation from one height to the other. In the next slide, you would see that how these all petrochemical and polymer industries are mapped on the surface of this world. There you see that most of the petrochemical companies, they are situated in this coastal city of Al Jubail. That is on the eastern province, and on the western province we have Yambo and Rabik, and on the south we have Zizan. This huge number of petrochemical complexes, they all reflect tremendous amount of growth in terms of education, business, training, commerce, and name whatever you would like to. It is a teamwork, it's a joint effort, and the leadership is provided by the royal family of this nation. Well, you know, this catalyst field, actually, it is about 70 years old, and it started with Professor Earl Ziegler and Professor Giulio Natta in 1950s. This catalyst research is an unending journey with unreachable destination. Now we have 20 petrochemical industries producing 16.25 millimetric ton per annum polyolefin, and this huge production volume ranks Saudi Arabia as the first and the fourth largest polyolefin producer in the Middle East and world. Therefore, Saudi Arabia should be an international polyolefin education, research, training, and business hub and leader. In the rest of my presentation, you would see that how we are doing to achieve this mission. This slide shows 6 hexagonals, and each hexagonal is representing a dimension or research unit that we have built since we started this journey in 1990. You can see catalyst evaluation and kinetic study, development supported catalyst and spacer, residual catalyst structure, catalyst active site distribution and microkinetics, drag reducing polymer and lubricant, and spherical magnesium chloride support. My emphasis would be in this area in today's talk, catalyst active site distribution and microkinetics. And these are the 2 blocks that you are seeing. They are our current industrial research activities and initiatives. So I would mostly cover this part and this part. The other parts, because of the shortage of time, I will not be able to address, but anybody interested from the audience can access me through my email. Now, pre-catalyst immobilization and polymerization rate limitation cause dormant and accessible catalyst sites, which means that whenever we prepare supported catalyst, all the active sites we cannot utilize. What is the reason? The reason is that the support itself, it works as a very big ligand. Now, we want that how we can model the distribution of the catalyst active sites. If we can do that, then we can always correlate the performance of our catalyst to the polyolefin microstructure and then processing and end-use application. The development of this modeling is based on 2 concepts. One is the Stockmeyer bivariate single-site molecular distribution and copolymer composition distributions, and the other is your Schulz-Flory distribution. So from the GPC and from the CRISTAF data, we have mathematical models. If we feed this data into those mathematical models, then we can generate the active site distributions inside the solid catalyst. Well, I see, this part, how I can do. Well, anyway, the model predicts, 5 active sites in our catalyst. What we did, we modeled it, and then we confirm the model using DSC experiments called SSA experiments, and the model and the experiments, they matched very well. We hope that our work will hopefully contribute to designing and developing enhanced supported later generation PO catalysts. By the by, a copy of my presentation I already sent to the organizer, and anyone interested to have a full copy of my presentation, you can either write me back or you can approach the organizer to have a copy for further reading. You know, the problem I'm facing is on the right side, I see the list of the participants that I didn't want. Now, the second part of the implication of this active site distribution is the development of this polymerization microkinetics. Chain termination regulates polymer chain ends unsaturations, which dictate post-synthesis functionalization, subsequent leaving polymerization, polymer degradation. Now, this model can correlate the chain transfer probability to the molecular of the active site, and that helps us to know what is happening during polymerization between the catalyst particle and the polymer particles. Please remember that here the catalyst particles disintegrate and the polymer particles, they replicate the shapes of the catalyst particles. Now, during this replication phenomenon, what is happening, it is very difficult to measure, but we have successfully correlated them through the development of these models and supporting the models through experimentation. And we hope that these results will contribute to develop future supported metals and catalysts that could synthesize polyolefin precursors having varying chain end unsaturations. Now I come back to the third application of this modeling active site distribution, that is your thermoxidative melt degradation and antioxidant formulation. You know that polymers are to be finally shaped into end articles, and the step that is in between, that is processing. And in processing, there is always melting and mixing with oxygen, and therefore thermo-oxidative degradation is always there. We have modeled that, and that we correlated with the active site distribution of the catalyst. And our model predicts your protection factor, antioxidant effectiveness, and S factor. And the model also, you can see on this side, it correlates very well with the experimental data. And now, what is the beauty here? The beauty here is that usually people would use, costly instruments like extruders, rheometers, and involved into complex rheometric measurements to evaluate the thermo-oxidative melt degradation and antioxidant formulation. But here we developed a very simple technique that is supported by experiments, but it originated from our deep understanding of this active site distribution. And we have predicted very well that from very simple laboratory experiments, we can tell how this polymer is going to behave during processing. Now, I would list some of the global challenges that this catalyst field is facing. After Ziegler-Natta catalyst, now we have metallocene catalyst, post-metallocene catalyst, and less transition metal catalyst. In all these areas, we need to develop robust multi-purpose enhanced Lewis acid spheroidal magnesium chloride support. At present, 9 companies are selling commercial grades of silica support, but in the entire world, there is no such commercial manufacturer of magnesium chloride support of varying properties and varying structures, varying Lewis acidities. So this is a very big void. If we can fill in this void, then this field would benefit the entire world much more. The second point is that this metallocene, post-metallocene, and transition metal pre-catalysts, they are highly active when we use the cage-structured methyl alloxane. This methyl alloxane, despite so many simulation studies, CFT studies, it is still a black box to the researchers in this area. And also it is very costly and it gels. Shelf life is less. Therefore, the next area that requires a lot of attention is the development of non-methyl alloxane standalone tunable co-catalyst formulation. So far, I was talking about one end, that is your polymers. Now, the other end of this catalyst field is catalyst-mediated base lubricant. It is a very huge field. Here, these chain lengths are controlled. It is not like, that of a typical polymer, 10 to the power 5 daltons. Here, it is maybe up to 30, 40, 60, 70, 90, or 100 carbon atoms, these lubricants. But the applications of the lubricants are huge. Here we need to develop product selective catalyst system and energy saving oligomerization process. Then third comes catalyst mediated drag reducing polymer. Here we need to develop particle formation processes. Drag reducing polymers, they reduce the friction of the flowing fluid. Then in the area of supported catalyst, we need to develop novel Lewis acid-rich oligomeric spacers and linkers, nano support and enhanced hydrophobic immobilization techniques, judicious application of unit operation concepts in catalyst development. I would like to mention a very subtle point here, that there is a collaborative research gap and lack of collaboration between chemists and chemical engineers. In the laboratory, the practices that are used to synthesize catalysts, to synthesize polymer, to support them, but in the industry, we need to do at a higher scale. So from the very beginning, if the unit operation concepts are correctly understood and they are applied and pursued, it can save huge amount of time and resources, and the process can be much more effective than if we miss this part. Next, this area, ethylene vinyl acetate copolymers, it has tremendous applications. The business is huge, but it is produced like low density polyethylene using free radical polymerization process, which is a very harsh process. The pressure is too high, the temperature is too high. Catalytic approach should be adopted in these areas so that mild to moderate conditions may be used to copolymerize ethylene with vinyl acetate. And my last one is oligomeric to polymeric impact property modifiers. With the evolvement and emergence of these new families of catalysts, we can produce, ethylene alpha-olefin and propylene alpha-olefin elastomers of different microstructures, and we can blend them to modify the impact properties of especially polypropylene, which is one of the very important thermoplastics in the polyolefin family. Now, I come back to our current research concentration. The slide shows to you that Saudi Arabia is currently producing about 150 kilometric ton per year. And by 2025, another linear alpha olefin plant will be established by Saudi Aramco. And so by 2025, the kingdom will be producing about 550 kilometric ton per annum of alpha olefin. Currently, most of these alpha olefins being produced in Saudi Arabia, they are being exported outside. So our research concern is that how we can develop much more value-added products using these alpha olefins inside Saudi Arabia. So we have the first two candidates. One is synthetic lubricant, and the other is drag-reducing polymer. Our research in drag-reducing polymer, it is much older, and the synthetic lubricant we started about a year. And these are the two areas we are focusing so that we can in near future come up with startup, and those startups can strengthen the economy of this nation. Here you see that Saudi Aramco is now operating 90 pipelines and 12,000 miles of crude oil, and it is importing about 2 million gallons, about 80 million per dollar of this DRA from outside. Our target is to synthesize, manufacture, and establish chemical plants that will produce these drag-reducing polymers inside this nation. And our university's location is very, very strategic compared to other Saudi universities. It is very close to the industrial belt of this nation. Therefore, we are focusing our research on this area that if we succeed, then this nation can build a future, not only in terms of industrialization, as well as development of human resources, and its dependence on oil economy will reduce further. This is the summary of the catalyst that we designed and also we patented. And this block is listing the concepts that we have used. They are pretty involved. Anybody interested can go through the slide. And this is our DRA research laboratory, and these are the products, and this is the evaluation of the product rig, DRA loop. This is our patent that we have done, and it's very interesting that this patent is giving us a catalyst that the as-synthesized DRP almost triples the rate of transportation of a selected grade of refinery product with a saving of total 50% pumping energy at ppm level pipeline concentration. Think about that. Now, what are the challenges? Development of in situ particulate morphology during polymerization. This is a major challenge. Then avoidance of very low polymerization temperature and lengthy reaction temperature time that we have done. Synthesis of more active catalysts that we are working on, and elimination of ground climbing and viscosity effects. And elimination of cryogenic grinding process, which is a very cumbersome process and cost involvement process that we want to eliminate by coming up with a polymerization process that will produce particles. Then we would eliminate that, and that would be tremendous breakthrough in this area. Now, you see, we are here today And from there, we want to move, and we want process intensification, energy conservation. We want to develop active catalyst, room temperature particle formation, enhance dispersion and control reactor release. And from there, our target is to establish spin-off company. Now, this is the last part of my talk, innovation diffusion spectrum. And again, it is a hexagonal, and it has 6 sides. Competitive advantages. They include new benefits offered, technical and financial advantages over existing technology, unique technology selling point. Second, observability. Awareness of R&D management and investor for the product and technology proposed. Unique performance offering high market attention and added value. Third, triability. Convincing performance evaluation in investor or customer facility. Our research is going through a paradigm shift. We are not typically interested, like, increasing the number of publications and high H index and so on and so forth. When I remark this, I don't mean that they are not needed, but that is not our top priority now. Our top priority is to gift this nation with very tangible research products that this nation will ever remember, and the economy of this country will continue to grow. Therefore, we are trying to learn, identify why an innovation fails to be accepted and marketed. That is the flagship statement of our research now. The fourth point is a solution better but similar to customers' current operation. Complexity, simpler and reproducible demonstration of benefits and more earning over a competitor. And this is the last and the sixth, perceived technical risk, safety, handling, sorting, and disposing. Well, these 2 slides, I tried to summarize that any research group that would like to do research thinking the way we are doing, that give your nation something that your nation would ever remember you. The economy will progress, more jobs will be created. Then these 2 slides would serve as a sort of guidance for my such colleagues. And this is our polyolefin catalyst research vision. We want to transform Saudi Arabia into an international hub and leader of polyolefin education, research, training, manufacture, application, and business. In this area, we are receiving a lot of cooperation from our university administration right now. We also received a lot of cooperation before. We are thankful and respectful to all our administrators. Now the university is expanding the number of courses offered in the area of polymers, and it has introduced MX course in polymers, CX course in polymers. It is also introducing a complete graduate degree in polymer science and technology. So our university is committed. This is my last slide. I would like to thank first SABIC, the Saudi Basic Industries Corporation, which is the prime mover to establish this polyolefin catalyst research in our university, our research institute, and in our center. Next, we are thankful to our university administration, then to my beloved research institute where I work, and the Center for Refining and Advanced Chemicals, Saudi Aramco, NSTPI Caxt. So SABIC, Saudi Aramco, and NSTPI Caxt, they have been constantly sponsoring our research projects. I'm very, very thankful. Whatever I presented to you as a spokesman on behalf of our research team and project team, the list is big. I cannot name all of them, but I am thankful to all my colleagues. And finally, I thank the MatScience Organizing Committee to give me the opportunity to present what we are doing in the area of polyolefin, what we have done, what we want to do in the future. But please remember, whatever we have done and whatever still remains to be done, the second part is much more than the first part. Thank you very much for your kind attention. I would be now available to address questions.
Thank you so much, Dr. Muhammad Atiqullah, for a wonderful talk. So the panel is open for the discussion. If there is any doubts, you can please ask Dr. Muhammad Atiqullah.
Can I ask a question?
Yeah, you can ask more than one.
Thank you very much. I'm Professor Zak from Israel, and I was very impressed about the talk. It is a little bit not my topic, but I do dealing with nanomaterials and also use them for lubrication and sometimes for improved properties of polymers. But I have just a question just to understand one small point from your lecture. Can you please explain what is it, drug-reducing polymer? What does it mean? What this polymer for?
Okay. These polymers are hydrocarbon soluble. They are amorphous. And their molecular weight is very, very high. They are called ultra-high molecular weight polymers. The molecular weights would be in the range of, say, 2 to 4 million daltons. When we mix or introduce into a flowing hydrocarbon, for example, crude oil or refinery products, then these materials add the proceed and we pump through the pipelines. Huge amount of energy is required there. To overcome the frictions, which is the main cause of putting so much of electrical and mechanical energy to push this material distances, you can consider thousands of miles. See how much energy is being used. And energy is every nation's concern. How can we decrease this energy? By injecting these polymers, I have shown that the consumption of the energy can dramatically decrease. So its practical value is too high. And Saudi Arabia is now importing these highly costly drag reducing agents from outside world, while the raw material and some of the catalyst preparation components, they are locally available in this country. And we have completed the project, we have patented, and we have acquired the technical know-how. Now we want to progress further that how we can achieve industrial level success. We have already identified the difficulties in these areas, and we also have learned how to overcome them. So if we can do them, then this will be a very big benefit for this nation. Am I clear to you?
Yes, I think it is very, yes, I didn't think about this problem even. So, yes, that there is a friction during, and you have to reduce it. So for liquid, I understood, yes? Okay, thank you very much. Thank you very much.
You're welcome.